In the vast landscape of engineering, few disciplines hold as much significance as materials engineering. Materials engineering is all about finding the best materials to use when creating anything. It is the cornerstone on which all of our vital technological advancements are made. Anything from the construction of spacecraft to the building of bridges has required the expertise of materials engineer. One of these fields where the influences of materials scientists can be seen the most is in the field of robotics. More specifically, in the creation of fighting robots for competitions like BattleBots, Robot Fighting League, Robot Wars, and many, many others. The machines that compete in these events are the results of hundreds of hours of design. Every part of these robots has a purpose, and nothing goes to waste. While it may be easy to be caught up in the wild weapons that are on display, one aspect of fighting robot design that is often underappreciated is the armor of the machines. You can have the greatest weapon in the world, but if it only takes a single hit to become inoperable, then there's a serious problem. Today, I'm going to be discussing the importances of materials engineering through the lens of designing armor for a fighting robot. Materials engineering is an engineering field concerned with the development and analysis of materials so that they can be used in the wider world. The creation of these new materials often involves altering the properties of old materials in order for them to fit a specific need or purpose. This could look like the creation of new kinds of steel in order to be stronger and bear more weight, or the development of new textiles that can be used in the creation of protective clothing for first responders. Another thing that materials engineers should be able to do is analyze a variety of different materials in order to find the best ones to fit a specific task. This could look like poring over data tables in order to compare the hardnesses of different materials, how conductive they are, how well they transfer heat, and other qualities that could affect their performance. This might seem pretty self-evident. After all, let's say you're making a bulletproof vest. Are you going to make it out of paper or Kevlar fiber? I mean, hopefully you'd choose the fiber, but if I were to ask you whether or not to use steel 4025 or steel BG42 for a helical envelope gear set, you might have a little more trouble coming up with an answer. This is where materials engineering comes in, and a materials engineer should be able to come in and tell you what the answer is, or at least be able to figuring one out. Materials engineers are essential parts of the broader engineering landscape, helping to design power plants and choose the right types of supports for bridges that are used thousands of times a day. On a basic level, there are mainly 4 types of different properties that materials engineers are concerned with when they look at a specific material. A material's mechanical properties, its thermal properties, electrical properties, and chemical properties. Mechanical properties are any properties of material that have to do with how well it behaves when under the influence of outside forces or loads. This could look like how strong the material is or how stretchy and elastic it is. Thermal properties are properties that have to do with how the material handles heat. Does it heat up fast, or does it heat up slowly, but then release that heat over a long time? Electrical properties have everything to do with how well the material conducts electricity. Certain metals like copper conduct electricity a lot better than non-metal materials like glass or plastic. Chemical properties have to do with the chemical makeup of a material, and it can involve things like acidity, toxicity, flammability, and other things. Of course, depending on what material you are analyzing and what its intended purpose is, it may affect how well each of these properties needs to be investigated or how important they are to the project. Let's take the design of a road, for example, and look at how a materials engineer might compare different materials. When deciding on what type of asphalt or pavement or whatever material they want to build the road out of, a materials engineer will need to look at these 4 different properties and of whatever the material they choose and see if it's a good fit for that situation. They'll look at the mechanical properties of the asphalt and see how much weight it can hold before it starts to deform. They will look at the thermal qualities of the asphalt and make sure that during the summer it doesn't melt, and that during the winter it doesn't cause the road to crack. They may also need to look at the chemical properties of the road to make sure that it's not toxic. But on the other hand, they may not need to look very hard at the electrical properties of a road surface, because conducting electricity isn't essential to the function of the road. We could do the same thing for the construction of armor for a BattleBot. The material needs to be strong and withstand some pretty strong blows. The material that is chosen for the armor needs to be analyzed in how well it conducts heat. The electrical properties of the armor, again, probably won't be that important. And the chemical properties are important to make sure that the material is safe to use and that shavings that fly off when it's struck are not toxic. Materials engineers also have to look at these different properties when they are making a new material as well, and must take into careful consideration how the different techniques and raw materials that they're using affect the final product. Understanding material properties and being able to make them work for you rather than against you is an essential part to understanding and mastering materials engineering, and without it, really nothing would be possible. Robot fighting events are usually bracket-style competitions where pairs of robots attempt to fight each other with the goal of rendering the opposing bot inoperable. All the robots entered into a competition are required to have at least some sort of weapon that can damage another robot. This could look like a hammer, a saw, a drill, mace, or even a flamethrower. There really aren't any restrictions on the types of weapons that competitors can use, as long as it's functional and safe. The robots are usually restricted in different ways to make the competition fair, like their weight and size, but many aspects of the robot's creation are left up to the team. Because of this, not only the weapons on the robots are vastly different, but also the shapes of the fighting robots, as well as the specifics of their internal circuitry and the different components, are very different in fundamental ways. Usually, many members of a team work together to design, construct, and control a robot that is used in a robot fighting competition. The building of a robot is an extremely intensive process that involves many different systems that all have to be in working order in order for the robot to function how it's meant to. As I said earlier, it's all too common for the focus of the design of these impressive machines to be on the weapons. This isn't to say that the weapons that are created for the robots aren't impressive. They take a certain extent of skills that are impressive in their own right, but the armor that protects the robots is often overlooked. The armor on the robots is one of those things where if it works well, practically no one will take notice. It's only when something goes catastrophically wrong is when the armor is mentioned. In a competition, good armor could be the difference between failure and success. The armor needs to be able to withstand extremely high forces and will also allow the robot to maintain its maneuverability and ability to fight back. It may seem far more simple to design armor for a fighting robot than it would be to make a weapon, or pretty much any other part of it, but in reality, the creation of armor for a combat robot is an extremely complicated subject that takes many different factors into consideration and can be just as complicated as building the weapon of the robot. There are many different factors that must be taken into account when designing the armor of a robot, but for simplicity's sake, I've narrowed it down to the 4 aspects of the armor that I think are some of the most important: the weight of the armor, its impact resistance, its durability, and the cost-effectiveness of the material that is being used. The weight of the armor has a huge impact on the overall function of the robot and can drastically affect the robot's viability in combat. The heavier and thicker a piece of armor is, it will most likely be stronger and more difficult to break, but it will also reduce the agility of the robot significantly, and this can have significant effects on how the robot might be able to use its weapon or avoid taking damage from the opponent. The opposite also applies. A light armor might allow the robot to be more maneuverable, but it may also severely limit its ability to survive attacks that it isn't able to avoid. Everything has its benefits and drawbacks, and especially when designing a critical component like armor, is it important to really understand what you're ultimately trying to achieve with your robot, and what you want the final product to be. The impact resistance of the armor is essentially just its ability to protect the robot from damage. Different materials will have different strengths when it comes to absorbing the force of attack. Materials will also have other characteristics that can affect whether or not it can be used, like its ability to deform when under stress. Some abilities may deform easier than others, bending or twisting the armor, as opposed to a material which may not deform as easily, but instead will simply fracture after reaching a certain threshold. A material which deforms may not be durable, allowing the armor to protect at least a little bit after it's deformed, while the more brittle an armor may protect it better until it fractures and then gives no protection at all. The durability of an armor is also extremely important to the usability of a robot. The armor needs to be able to withstand multiple hits from an opponent's weapon. This can be affected by how thick the armor is and how strong the material is in general, but it can also be greatly affected by whether or not it deforms as well. Having durable armor that allows the robot to survive an entire fight is an extremely important part of the competition. Competitions are very frequently decided by robots' ability to survive a prolonged fight. It is very rarely decided in the first few seconds, and having armor that can last several minutes of intense combat is often the deciding factor in a fight. Having a durable armor can also help to reduce the cost of having to replace the armor after every fight. Depending on the material that you're using and how specialized the part is, the price for replacing the armor can be extremely expensive. Many of the teams that are involved in robot fighting competitions are made up of hobbyists, not professionals, meaning that they very rarely have an enormous budget that can be spent solely on the armor, especially when many of the fragile internal components of a robot need to be frequently replaced and are often much more expensive. Over time, the designers for the robots have settled on a selection of materials that are generally considered to be the best for the construction of armor on BattleBots. One of the most common materials that is used for the construction of armor is unsurprisingly steel, one of the most commonly used metal alloys throughout the world. Steel is an extremely common and strong, also very durable, making it a very safe choice for a variety of situations when designing armor. Steel also has a huge number of specific different alloys that all have unique characteristics because of the different ingredients that are used to make them, as well as how they are treated after the steel is made. As I said, steel is one of the most common alloys, and it is pretty cheap depending on the variety that you're getting. Really, the only downside of steel is that it can be relatively heavy, at least when compared to other metal alloys like aluminum. Aluminum alloys are different from steel in that they're far less strong and durable, making them a relatively ineffective choice for armors that need to take a big hit. Where it makes up for this lack in strength is in its lightweight, allowing it to be used on smaller robots where the goal is to make it fast and agile. Other metal alloys that are commonly used are magnesium alloys, which are decent middle grounds between steel and aluminum, providing a decent amount of strength and durability while also being pretty light. In theory, this would make the ideal choice for many different situations, but because of its rarity, it being much more rare than steel or aluminum, makes it quite a bit more expensive to the average consumer, meaning that it is really only a viable solution for large professional teams that are capable of getting a lot of it. Similar to magnesium in that degree are titanium alloys. Titanium alloys are some of the strongest and lightweight that can be used on the robots, surpassing even steel. Its downsides are that it's also significantly more expensive to buy than the average steel or aluminum. It is important to note that a good designer of a fighting robot will also be able to use a variety of different materials when making the armor, mixing lighter materials like aluminum on parts that can afford to be damaged slightly, while using stronger materials like steel or even titanium to protect essential components. Using a combination of metals allows for the robot to maintain a decent weight while also being sufficiently protected. To take a further look at how all of these different components of materials engineering and armor design interact, I decided to try and make my own armor for a fighting robot. The entire goal of this project was to try and understand a little bit about the process that goes into making such a complicated piece of equipment. The creation of the armor would have to be broken up into several different steps. First, I would need to make the actual robot that I'd been reinforced. For this part, I looked online and got a simple kit for a remote-controlled robot that had an arm. The reason that I chose to buy this kit online instead of completely making one from scratch was primarily due to the fact that it would be far more cost-effective than buying all the materials myself and then machining the individual parts, especially since I have no materials or whatsoever to build a project like this. Anyways, after the robot is completed and functional, I will need to identify parts of it that are the most exposed and important to protect. The next step is to design an actual piece of armor that can protect it, as well as deciding on material that I will be using to make it. After running simulation and analyzing the effectiveness of my design, I might redesign it in order to improve it. So with all that in mind, it's time to begin. Here's the final project of the small robot that I bought. While I did not design it myself, I still took the different qualities of the robot into account when deciding on what I was going to buy. There are three main qualities of the robot that I noticed when deciding on this one. The first is the large amount of material in the front of the robot. In the actual design, this part consists of several different motors, a camera, and sensors, all of which are unnecessary for the robot to function in the hypothetical situation it would be in. In the case of how I'm using it, this extra material functions as a shield protecting the front from damage. The laser-cut polycarbonate plastic will provide a good amount of protection on its own, allowing me to avoid having to design protection for that part, which would be particularly tricky to fit, given that such particular geometry. This also gives more protection to the front of the robot, which is the area of a fighting robot most commonly struck during a fight. The second part of this robot would be to notice its use of treads on the robot instead of wheels. Treads are extremely useful for applications that involve difficult terrain. While in the beginning of a match there is usually very little to prevent movement, after a battle is well underway, the area becomes very quickly littered with debris that can cause problems for wheeled robots. The tracks also allow for more torque to be put into the ground, reducing sliding, especially if the goal of my robot is to move quickly. Treads are also used more durably than wheels in many cases and can withstand several strikes before breaking. The final part of the robot that I looked at was the arm. As I said before, in order to compete, a robot must have a weapon that is capable of damaging an opponent. While in its current state as a grabby thing, it can't do this. It would be pretty simple to transform it into something that could be capable of maybe doing some damage. Now that the robot is completely finished, looking at the exterior, it's pretty clear that the most important part of the protect would be the Raspberry Pi that is being used to control the whole thing. This is by far the most expensive component, and I really don't want to buy another one. You can see that the back of the robot is completely exposed. Ideally, I never want to be facing away from an opponent in the middle of a fight, but sometimes stuff happens and would be a pretty appealing target for an opponent. Another area that is very exposed is the arm of the robot. The wires from the servos could be damaged pretty easily, and even a single strike to the servos could result in the loss of function in the arm. However, with the current design of the arm, it would be nearly impossible to armor them, as it would limit the very small amount of mobility that it already has. With all this in mind, the armor that I will construct will primarily be focused on protecting the exposed portion of the Raspberry Pi in the rear of the robot, and I will try and find a way to minimize the exposure of the servos in the arm without using bulky armor. Now, it's time to start designing the armor of the robot. My first instinct on how to do this was to model the parts of the robot that I would need to be protecting, and then work out a good way to design the armor around them. Here's the completely painless process of doing just that. Now that the model is done, I can fit the armor perfectly to the exterior of the robot's chassis. The main limitation of this design is the arm and the treads. The distance from the treads to the main chassis is only a dozen or so millimeters. This means that the sides of the robot will be pretty thin and may not be very strong either. It is important to note, however, that the thickness of the armor can have a negative effect, as I said before. It can make the robot, which is already slow, much slower, and will not be able to cool itself easily, an issue that the robot already has a problem with. With this in mind, I'll design my armor relatively thin and take the problem of heat conduction into account when later deciding on material that I'll be using. So you can see from the design that I settled on is light, as I could make it while still being thick enough to actually make a difference and hopefully protect it from several strikes. Now it's time to decide on the material that I'll be using. The main materials that I'll be focusing on are aluminum, steel, and titanium, but I'll also be looking at plastics and magnesium alloys as well. To begin with the analysis of the different materials, the first thing that I did was to simulate an impact with the armor being made of these different materials. This was done in SolidWorks' drop test simulation. The reason that I chose to use a drop test instead of other simulation types that show stresses on an object was because the application of the part that I'm designing is very specific. It must be able to withstand an impact and not simply bear a load like other parts. And while the drop test cannot perfectly simulate this impact, it is a better approximation than applying a static force to the armor. I ran my simulations with an impact velocity of around 250 miles per hour, the highest tip speed of a swinging weapon in the BattleBot tournaments. Here are the results of my simulations. Aluminum alloys, titanium alloy, the steel alloy, for the magnesium alloy, for the polycarbonate plastic, you can immediately see that some of these materials would simply be unusable, namely the polycarbonate, the same material as the body of the robot. This program doesn't allow for the fractioning of the material, so in a real-world scenario, the plastic would most likely have shattered before it would have deformed to such a degree. We can see also that the magnesium alloy was subject to a large amount of deformation as well, making it an unlikely candidate for the final choice. Unsurprisingly, the aluminum also experienced quite a large bit of deformation, as well as experiencing the highest amount of von Mises stresses, falling well beyond the absolute yield strength of the material, meaning that if an armor made of this material to actually be impacted, it would break beyond repair. This would be the same for the steel alloys that I tested as well, and would likely not be able to withstand an impact of this velocity without fracturing. This is, of course, the highest velocity possible, and so it would be completely reasonable to assume that in a real fight, the robot would never come close to having to withstand an attack like this. Now, it's time to take a closer look at the individual properties of these materials and compare them. First, let's compare steel, aluminum, and titanium. For the titanium alloys, I chose TI6AL4V grade 5 and TI5AL.25N. The names of these alloys are determined by the different materials that are made up of Ti for titanium, Al for aluminum, and so forth. For steel, I chose steel 1018 and chromoly, or steel 4130. The names of these alloys are based off of AISI and SAE indices that outline how the steel should be named, with the first two digits detailing the types of alloying metals present in the steel, and the last two being the percent of carbon in the alloy. For the aluminum, I chose 6061 T6 and 2024 T3, their names also being determined by AISI and SAE matrices. I chose these specific alloys because of their popularity in fighting robot design, as well as their availability to the average consumer. Initially, looking at steel and titanium, we can see that for these specific alloys, steel in this case is significantly more dense, to the factor of about 1.75. Looking at the different hardness scales, we can also see that titanium is almost 3 times as hard as steel. The tensile strengths of these materials follow this pattern, with the tensile strength for titanium being significantly higher than that of steel's. Looking at the thermal conductivity of these materials, however, we can see that steel is a lot more thermally conductive than titanium, something that could affect the Raspberry Pi's ability to cool. Now, if we compare the steel to the aluminum, for these alloys in particular, we can see that something surprising, as while the aluminum is about 3 times less dense than the steel alloys, the hardnesses of these two materials were almost the same, with aluminum never surpassing, but only remaining slightly below the steel. However, aluminum's ability to conduct heat far outshines steel's, being almost 3 times as thermally conductive. Looking at these different qualities, we can see that in terms of raw strength, the titanium far surpasses both the aluminum and the steel, making it the best choice if I were to consider simply which would protect the robot the best. The only area where the steel surpassed the titanium was considering its ability to transfer heat, but when looking at that quality in particular, we can see that the aluminum is far better. Also, even though these types of aluminums were far less dense than the steel, their hardnesses were comparable. With all of that in mind, we can clearly see that in an ideal situation where I had all the money I wanted, if I were trying to make the most protective armor, I would probably pick the titanium alloys. On the other hand, the aluminum alloys would work excellently if I were trying to maintain a lightweight while also be able to make the computer cool. Realistically, however, the aluminum alloys would likely have to be my final choice, simply due to the fact that titanium is extremely expensive, while aluminum alloys are usually far more manageably priced. Looking back on the project now, it's evident that materials choice played a pivotal role in determining the performance and effectiveness of our BattleBot. Throughout the design process, we recognized that the materials selected would directly influence various aspects of the bot's functionality, including its durability, speed, agility, and overall combat capability. In our case study, we observed firsthand how the choice of materials significantly impacted the bot's performance. For instance, opting for lightweight yet durable materials such as aluminum for armor allowed us to achieve a balance between strength and agility. This choice hopefully would enhance the bot's maneuverability in the arena while still providing adequate protection against opponents' attacks. Reflecting on our experience, several generalizable principles for material selection and engineering design emerge. Firstly, understanding the specific requirements and constraints of the project that you're making is essential. Whether it's the need for lightweight materials in aerospace applications or the demand for high temperature resistance in automotive engineering, aligning material properties with project objectives is paramount. Secondly, conducting thorough materials testing and analysis can provide valuable insights into performance, characteristics, and potential failure modes. By leveraging tools such as finite element analysis and mechanical testing, engineers can make informed decisions and mitigate risks associated with material selection. Beyond the realm of BattleBot design, materials choice holds a significant importance in various other engineering fields. In aerospace engineering, for example, the selection of lightweight yet robust materials like titanium alloys or composites is critical. Similarly, in the medical device industry, biocompatibility with materials such as medical-grade polymers or stainless steels are essential for ensuring patient safety and device reliability. Every aspect of material must be considered, and the consequences for failing to do so could mean the differences between life and death in many scenarios. In the world of BattleBots, where every component plays a crucial role in determining a robot's success or failure, the choice of materials for armor design is paramount. Our exploration into materials engineering has revealed that the performance, durability, and overall effectiveness of a fighting robot heavily relies on the materials selected for its armor. By carefully considering factors such as mechanical properties, thermal conductivity, and cost-effectiveness, engineers can optimize armor design to withstand the rigors of combat while maintaining the robot's agility and functionality. The principles and insights gained from our study extend far beyond the realm of BattleBots, resonating with various engineering disciplines and real-world applications. From aerospace to automotive, medical devices to consumer electronics, materials choice plays a fundamental role in shaping the design, performance, and sustainability of modern technologies. By harnessing the principles of materials engineering, engineers can innovate solutions that meet the diverse needs of society, while pushing the boundaries of technological advancements. As robotics continues to evolve and integrate into various aspects of our lives, the role of materials engineering in shaping the future of robotics cannot be overstated. Advancements in materials science, coupled with cutting-edge design techniques, promise to unlock new possibilities in robot performance, efficiency, and adaptability. From lightweight yet robust materials for agile drones to flexible and durable composites for humanoid robots, the future of robotics is intricately linked with the innovations in materials engineering. By embracing the interdisciplinary collaboration and pushing boundaries of materials science, engineers can drive the next wave of technological breakthroughs, ushering in a new era of robotics that enhances human capabilities and transforms our daily lives for the better.